The fallback when the limit comparison test doesn't work is called the limit comparison test. So I've written it down here. It says if you have two series, call them A and B. They have positive terms, which everything in section 8.3 does. And you let C be this limit. So we define this. You're going to say let C equal the limit and figure it out. If that number you get is a finite positive number, then the series both converge or both diverge. So that means you want to take what you start with and what you want to compare it to. And then they'll act the same. You want to compare it to one you know. Just like with the comparison test, we don't choose one ahead of time, we just see what falls out. So let's take this series that's almost the same as before, 1 over the square root of n squared plus 2. Just like before, I'm going to look at the general term I've got, 1 over square root n squared plus 2. I'm leaving sigma behind. I compare it to 1 over the square root of n squared because the 2 doesn't matter when n is a billion or trillion. And if I'm dividing by something bigger, I'm getting something smaller. So this is less than or equal to. And on the right side, it simplifies to 1 over n. We know that 1 over n, if you take the series, is a p series. So the p-test says that it will diverge, which means the one we're curious about is smaller than something that diverges, so it doesn't tell us anything. All we know is we're smaller. But if the world is just, then it should still act the same because that plus 2 really shouldn't matter that much. So we're going to use the limit comparison test. So we're going to think inequality is backwards. So let's use the limit comparison test. To use the limit comparison test, this is the line we really need. We're going to let C be the limit as n goes to infinity of the fraction. On top is the series we started with, 1 over root n squared plus 2. And on the bottom is the new series that we were going to compare it to, 1 over n. So we still start with the comparison test because it still did some work for us. We're going to divide by this fraction, so we flip and multiply. That's the limit as n goes to infinity of n over the square root of n squared plus 2. I can't really cancel anything super nicely. The square root causes trouble. There are dozens of ways to fix this, and you've probably done it before. You might think L'Hopital, you might think all sorts of things. I'm going to use an algebra trick. So this is the limit as n goes to infinity of the square root of n squared over the square root of n squared plus 1. So this is our trick that you don't have to understand, and if you do, great, and if you use it, great, but who cares in the long run? The square root of a fraction you can combine. This is the limit as n goes to infinity of the square root of n squared over n squared plus 1. The square root is continuous on its domain, so we can bring the limit inside. So that's the limit as n goes to infinity of n squared over n squared plus, my 2 changed to a 1. Or, yeah, let's change that back. N squared plus 2 inside the square root. Now, if we take the limit, we just have, you could use a rational function, you could use leading terms, you could multiply by 1 over n squareds. Again, it doesn't really matter how. That's the square root of 1, which is 1. Which means C equals 1. So we check, is that a finite number? Yes. And is it bigger than 0? Yes. So, by the limit comparison test, they are the same. That's what we're thinking. They both converge or they both diverge. So again, we know that the series 1 over n from n equals 3 to infinity diverges by the p-test with p equals 1. So by the limit comparison test, the series 1 over square root n squared plus 2 from n equals 3 to infinity also diverges. Okay, we have to see something that tells us what our limit was, and you have to state why the one you know converges or diverges does so, and then what that tells you about the one you were actually investigating. Okay? Again, you start with the comparison test. And then, if it didn't work, if the inequality was backwards, that's the key. When it's backwards, we use limit comparison test. This was the term we started with on top, and on the bottom we just had the term we wanted to compare it to. I hope that clears up these two tests and you see when to use which. And notice we're really not going to integrate much anymore because they pretty much all turn into limit comparison tests and comparison tests. Have a great Monday, Tuesday, and I'll see y'all later.